Hello and welcome. The purpose of this video is to walk through Key Assessment 1 that we took on September 10th, 2021, our first key assessment of Year 2, IB Chemistry. And I'm just going to walk through all of the problems I've combined high level and standard level here into the same document and video as you can see. So just pay attention to whether or not the problem applies to you. So we'll start off with everyone. Everyone's first question was to name a mechanism for this reaction. Yes, this is an example of halogenation, but as we've seen a couple times, including T5 homework 8, number 9, the IB only accepts the general category, the addition. Addition would apply to hydration, hydrogenation, halogenation, all of those different reactions we learned where you can add things across a double bond. The type of reaction for all of those cases is addition. And we've seen that in several different homeworks, most recently T5 homework 8. All right, moving on to high level only aiii, aiii. So stating the major product, we went over Markovnikov's rule again on August 27th, stating that hydrogen tends to bond where there are other hydrogens. And so many of you realized that if I had HBr, which I know you needed to change on your test, that it just said bromine, but most of you made that change. If you had HBr, well, HBr would indeed, the Br would go to the second carbon. So many of you had 2-bromobutane. I did see some issues with numbering. Notice the 2 must be in front of bromo. Some people tried to put bromo 2-butane. Well, that does not make sense because the 2 would not apply to what comes after it. So it did need to be 2-bromobutane, just like we saw on March 4th, way back when we were studying organic naming. All right, another high level only problem, aiii. So Markovnikov's rules. So remember, way back when, in second semester of year 1, we learned Markovnikov's rule in terms of hydrogens. But on August 27th, in high level time, we talked about how the explanation is a little bit more complicated. On your final, I accepted an explanation about hydrogens being more likely to attach where there's other hydrogens, but we discussed that that's not the complete explanation. And moving forward, I would only accept what the IB actually accepts. So we struggled a little bit with this question. The reason that Markovnikov's rule works is because of the stability of the carbocation. So I know that a secondary or tertiary carbocation is more stable. And so when I form that carbocation intermediate, if I were to add my Br plus here, this carbon would have been a carbocation intermediate versus this carbon being a carbocation intermediate. Well, which is most stable? Well, the one with more alkyl groups attached, because we know alkyl groups stabilize a carbocation. Carbon really does not like being positive. It needs help from other carbons to distribute that charge. So you need to say something about increased carbocation stability, carbocation stability as reasoning for Markovnikov's rule, not just stating the rule. And this is an update from what you saw in your final. All right, the next question was the mechanism. We did okay with this. Make sure that you're showing the arrow going from the double bond. Arrows always start from some sort of negative area of some sort. Arrows always go from nucleophiles, from something that's negative. So the arrow should go from the double bond to the thing that's partially positive, and then the rest of your molecule leaves. So you did need to show both of these arrows to get that 1 point. And then this is just an example from what we saw in class. This was from high level August 27th, slide 26. Of course, you were using uh, butene, right? You started with butene. So you should have more carbons than they show, but I'm just focusing on the mechanism part. So you needed two arrows to get that first point. You then have a carbocation intermediate, which we just talked about with Mark-Novikov's rule. And the negative thing that you just lost here is going to attack that carbocation intermediate, and you'll form a product. All right. And the next question was comparing SN1 and SN2. We've seen lots of examples of this. This was one where I was a little bit generous. Some people put two similarities and one difference. Some people put one difference and two similarities. The actual question said two similarities and one difference. I know this was a really, really tough test, and I wanted to award as much knowledge as possible. So I don't usually do this, but I was a little bit generous, went a little bit off mark scheme occasionally, if you gave some sort of valid comparison. So similarities, both nucleophilic substitution with a halocane and OH minus. You might have talked about the type of attack. You might have talked about transition state versus an intermediate. Lots of people mentioned the solvent. Some people mentioned the rate. Some people mentioned 2 steps versus 1 step. We, of course, saw way back when in May the same information again. Both nucleophilic substitution, halogen alkane to alcohols, and then lots of options here for ways that you could compare SN1, SN2. All right. Question B there, we saw this in HL time on August 27th when we were finishing up organic chemistry. And this was just one of those conditions that you needed to memorize. NaBH4 is the solvent to go from an aldehyde to an alcohol, or the conditions to go from an aldehyde to a primary alcohol. Specifically, the best word to use there is it's the reducing agent. A few people got confused with other reducing agents or with oxidizing agents if you're going in the other direction. So as we talked about, this was just a little bit of memorization. Maybe you're laughing that it's actually more than a little bit. All right, the next question was about, let's just double check, part B there. So we've done this one. The next question should have been about an equation for complete combustion. So let's keep moving forward here. Okay. So complete combustion and, oh, okay, sorry. So part B from SL, so we've just done part B from HL, part B from SL. Part B from SL was about writing an equation, basically the same thing that we were talking about here in HL time, which you might have skipped in the video, but writing an equation for haloalkane plus OH minus for nucleophilic substitution. You've, of course, seen that in lots of places, but the most recent time you would have seen that was T5 Homework 8, very recently actually, where you had to write an equation for a haloalkane. Chlorine in the homework, you had bromine in your test, and NaOH, or you could have just done OH minus. Notice that we're showing structural formulas here. You could have shown condensed structural or full structural, showing either the ions or the complete reactants. All right, next question, and this one was for everyone. We're back to everyone. Question C, day 7. Okay, complete combustion. We've seen that lots of times. The first time we saw it was way back when in organic, of course. Many of us did this well. Some of us need to work on balancing. If you're in that boat, there's some videos in the topic 10.2 homework doc. There's some videos that can help you out if you're still struggling with balancing. Most of us are good, but a few people still need to work on that. All right, the next question you had was enthalpy of combustion of the organic product using section 12. Okay, so this gets into topic 5, finally, right? So you saw practice of this here, topic 5, homework 8. Recall, when I'm using section 12, that's going to be enthalpy of formation data. It happens to be for a combustion reaction. That's really common, but I'm still using formation data. That means each of my intermediates are going to be the elements that form my compound that I'm interested in, my compound that I'm actually going to find in this reaction. So C2H5OH, O2, CO2, H2O. Of course, you had a slightly different organic um, substance that was combusting in your test, but same idea. All of these things are in the products for these intermediate equations. What does that mean? Well, the molecules that are in my reactants in the equation that I'm actually calculating the enthalpy change for, so my reactants here, these will need to switch signs. And we showed that here. This was from your homework, and again, your test should have been exactly the same thing, that your reactants switch signs, CO2 and H2O do not. The other thing I wanted to mention there, most of us realize this, oxygen, this is elemental, and so delta H of formation equals 0. You also did need to know this 241.8 number. Some of us wanted to use the formation for H2O liquid, but as we talked about in T5 homework 8, you do need to use the H2O gas, and that's what we used in both of these problems. Someone even asked that question in the homework document. Do we have to know that CO2 and H2O are produced in gas in a complete combustion? And yes, you do, because in a combustion, your products would both be in the gas form because a combustion reaction has high temperature. So some of us got a little tripped up on that. Make sure that you're not using H2O liquid, but you're using H2O gas in a combustion reaction. All right, moving on. Next question, bond dissociation energy. So energy required to break 1 mole of bonds in a gaseous state. You did need to name that it was a gaseous state. We've seen this definition a couple times. This was a HL slide. This was a SL slide or core content. So again, if it's underlined, it's probably important, right? We talked over and over again about the states and how that matters for enthalpy. So many people lost a point here for not saying gaseous state. Some people wanted to say standard conditions. Well, that doesn't really make sense, right? Because we know standard conditions are 100 kilopascals and 25 degrees Celsius. Not everything would be a gas at these conditions, right? Pressure and temperature, that's what determines the state that something's in. And we even saw that in section 12 of the data booklet. At standard conditions, plenty of things exist as liquids or even solids. And so if everything is in a gaseous state, by definition, you cannot also be in standard conditions. So this is the correct definition, and not saying anything about standard conditions or SDP, because that would not make sense if everything needs to be in a gas. So paying close attention there. All right. Next question, civ. Let's just double check which question that was. And this one was for everyone. Outline whether bond enthalpy values would be valid in CI. Well, notice they told us that this guy here was liquid. They told us it was liquid, that my alcohol was in liquid. And so for the reason that we are just saying, no, because it needs to be in liquid form. And we had actually just seen a question like that. You could have gotten that just from the definition, but we'd also just seen a question like that in T5 day 9, where we saw bond enthalpy values are not valid if not everything is a gas. So you just got a chance to practice that. All right, DI was calculating bond enthalpies. I know in high level, a couple people missed this problem. I know there was not a space here. Let's see if we can show what the DI looked like. I know there was not a space here, and I feel bad about that, but it's really, 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 really important that you're reading closely in every single IB problem. You can't miss any words like we just saw with the information about it being liquid. And so make sure you read closely. Many of us realize that there was a DI problem here, but some of us missed that. So determine the standard enthalpy change for this reaction using section 11 of the data booklet. Well, that's just a bond enthalpy problem. And so we practiced that here the day that we did bond enthalpies, which was T5 day 9, when we practiced drawing out the molecules and then putting together the bond enthalpies. So that just involved drawing the molecules, counting the bonds, and looking up the correct bond enthalpies. The things that I saw there is some people forgot that oxygen has double bonds. We saw that in our bonding unit. Sorry, just carbon dioxide. Some people also forgot that carbon dioxide has double bonds. And so you needed to look on the bottom of section 11 to find the C double bond O and the O double bond O values, not the CO or single bond O values. So that's where people tended to get tripped up here. Other than that, people did pretty well, remembering that bond enthalpy is an example of reactants minus products, unlike formation. Okay. And then outline why bond enthalpy values are not valid in calculations. Well, or outline their limitation. Well, that has to do with the fact that bond enthalpies are averaged for multiple compounds. And so it's not specific to the compound that you're dealing with. Okay, moving on, question 2. So question 2 involved 2 steps. You had 5, and this is the high level question 2, I should say. You had 500 grams of air, 0.5 moles of phosphine. You had a enthalpy of phosphine, and then, of course, information about air, the specific heat, I should say. So the first step was using this data here and using the standard enthalpy as a conversion factor to find the enthalpy change from phosphine. So to find Q, we saw that idea of using the standard enthalpy values as conversion factors a couple times. We saw that here in question 7 in T5 homework 5. We also saw it in T5 homework 8. We saw that idea of using a conversion factor. And I even wrote, here's what the conversion factor setup would look like. And we used the energy that we'd found from the reaction as a conversion factor. So that should have felt familiar. That was the first step in that problem, was to do a conversion factor, moles, 0.500 moles of phosphine. Notice you didn't even need to know what phosphine was. You didn't need to know a chemical formula or anything like that. For every 1 mole of phosphine, you release negative 750 kilojoules. So you should have gone negative 350 kilojoules as your enthalpy change. Now, if you imagine your phosphine was the thing combusting, phosphine, and then the energy was released into the air. That's very, very similar to the problem that we saw here with the spirit burner. With the spirit burner, we were dealing with water instead of air, but you should have been able to apply that same idea. So then we take the energy that was released from the phosphine, we assume it all went into the air. I can say negative 350 kilojoules equals. Now, here's where you need to be careful. If I'm using kilojoules, I need to use kilograms. 0.500 kilograms times 1, and I see that just right here in the units. I need to make sure my units cancel. 1 kilojoule per kilogram K, and then delta T is my unknown there. You also could have done joules and grams. So I could have had negative 350,000 joules equals 500 grams times 1 gram per, or joule per gram, excuse me, joule per gram, degree Celsius, or degree K, doesn't really matter, times delta T. But I needed to make sure units canceled. Kilojoules with kilojoules, just like we see here, kilojoules with kilograms, excuse me, or joules with grams. So all of stoichiometry was learning about units canceling. You need to write your units in your work because then you'll be able to see if they cancel like you expect them to. So that's how you set up that one. Again, very, very similar to this problem. For those of you who are in standard level, well, this problem here is exactly the same as the one that you had on the assessment. All right, question 3. Question 3, standard level and high level. Everyone had the same problem here. Determining limiting reagents. Seniors, you need to know how to determine limiting reagents at this point. I saw a lot of people struggle with this. I saw people not calculating theoretical yields. I saw people trying to use grams when we had solutions. If you're confused about this, you need to come talk to me. It's time to get this figured out. It's past time to get this figured out, really. We're going to see stoichiometry for the rest of the time we're doing IB chemistry together. So it's really, really important that you're going back to what we did in stoichiometry and working through that. All right, B and D. Where did we see B and D? Well, we saw that in T5 homework 5. So I should have seen this is an example of aqueous, right, plus solid. When I have aqueous plus solid, the mass that I use is my mass of solution in Q equals MC delta T. I saw some people trying to use this 4.5 grams. That's not the mass of my solution. 150 cubic centimeters, I use a density of water to make this 150 grams. This is the mass that I should have been using. Specific heat, of course, specific heat of water. And then the assumptions we make. Well, we make the assumption, of course, that the solute did not significantly affect the specific heat of water, and that the solute also did not affect the density, so that 150 cubic centimeters to 150 grams was valid. Some people didn't mention that it was the solute and water, so make sure you're being really specific there. C, the major source of error in all calorimetry. We talked about that various times. One time was in our warm-up on T5 day 6 when we did this whole thing on heat loss, and we said that heat loss always, always, always makes T final lower than the true value because heat is always lost. We talked about it earlier too, but that was probably the most recent time you saw that. All right, question 4. Question 4. For SL, I ended up throwing out because this in the SL document said lactic acid. Sorry about that. No one asked me about it during the test, so I didn't correct it during the test. But the idea here was to find find hexanoic acid. So hexanoic acid, hex, I know I'm going to have 1, 2, 3, 4, 5, 6. 6 carbons, I should know from organic chemistry. Oic acid is a carboxylic acid, so it always has this end. And then I fill in my hydrogens. Some of us are trying to draw full structural formulas without being explicit in all of our atoms. Make sure you fix that. So C6H3, 4, 5, 6, 7, 8, 9, 10, 11, 12, O2. Hexanoic acid. All right, so this wording was a little confusing, but read carefully. Determine the standard enthalpy of formation of hexanoic acid. So I need to write the formation of hexanoic acid, which is going to be 6C plus 6H2 plus O2 yields C6H12OH using section 13, which is combustion data. So now I need to go find delta H combustion, delta H combustion. This was the only tricky thing. We had never mentioned this in class, and I was super happy that a lot of people realized this. For oxygen, your delta H of combustion is 0 because combustion, of course, is reacting with oxygen. O2 plus O2 don't react, right? Delta H combustion, and then I just use these values that I find to calculate my enthalpy of the for this reaction. We practice that. We practice writing those formation equations here on T5 day 8, and then we practice using combustion data to find enthalpy of a reaction in that same day on T5 day 8. All right, and then this question was very, very similar to question 5 in T5 homework 8. So if you take a look at question 5 and T5 homework 8, it was the same thing. We had to write the formation. We then found the combustion for each one. And then you'll take a look and we used the reactants, combustion data minus the product combustion data to get enthalpy for this overall reaction. The only difference on the test was this was not separated into A and B. You had to know that, of course, to find the enthalpy change for the formation of your molecule, which in our case was hexanoic acid, well, that meant that you had to actually write the formation of hexanoic acid. All right, question 5. I'm a little concerned here because not a lot of people got this, and we saw this in topic 4. We saw this on the final exam. The most recent time you would have seen this is in your final exam rework. Whenever the IB asks you to describe ionic bonding, you need to say electrostatic attraction between oppositely charged ions. People are telling me all sorts of crazy things here, or not crazy, I shouldn't say crazy, but people are saying all sorts of things here. They were talking about the electrons and how they move, kind of looking at it more from a grade 10 perspective. But you should know by now that what the IB expects is when you need to describe ionic bonding, you describe it with electrostatic attractions and oppositely charged ions. People did really well with B. I was really impressed. Again, very similar to what we saw in our final with question D here. And so, yep, people did well with that. Sorry, I thought I had something here. What we should have seen is increasing and a big jump between 2 and 3 because SR is in group 2. And we'd seen that in part D of our final exam rework as well. We'd also, again, just really, really harping on that point of ionic bonding. We had just seen this in lattice enthalpy. So we talked about electrostatic attractions between ions, and the other part of this question, that the bonding and structure, well, the structure is lattice. Isn't that the whole thing that we studied in high level? So some of us mentioned lattice, some of us didn't. So I was hoping we'd make that connection because it was from something we had done really recently in high level time. Lattice and electrostatic attraction and oppositely charged ions for A. B, plotting ionization energies. We should remember this from periodicity. All right. C and D, you would have really found from using that Born-Haber cycle video that we made, the Born-Haber cycle video, where I walked through this problem. I walked through how all of these are equal to lattice enthalpy. Notice how the arrow for lattice enthalpy is from your ionic product to your atoms. Lattice enthalpy is always endothermic. The only thing that people really got tripped up on here was that in the problem that they gave you, I don't know if I've drawn it now, but in the problem that they gave you, the lattice enthalpy, they gave it to you going in the opposite direction. So you had to switch the sign. E, the issue that I saw people having with E was not being specific about, so sorry, this should be E. The issue that I saw people having with E was not being specific about which ions. Some people wanted to talk to me about SRO and CRO and then say the word ion. You needed to prove to me that you know these are not ions. These are ionic compounds. And the ions that would separate out are SR2 plus and Ca2 plus. So you needed to mention the specific ions. If you're going to talk about ions and ionic radius, you should mention the ions that you have. So that's where people lost some points there. You would have gotten this from HL Homework 1. You had to do some reading and some summarizing. Also in the mark scheme, I wrote this out for you. So notice that when I was describing the relative size of the ions, I was actually mentioning the full ion and not the whole compound. All right, last little bit here, question 5, SL. This was just a basic Hess's law problem. We saw that on slide 21, T5, day 6. We did this together in Jamboard. I also made 2 whole videos on Hess's law. So if you're not sure about how to do Hess's law, go back to these videos and that will help you out there. And then in part B, this was very similar to the problem that we saw in T5 homework 5, where instead of having to calculate enthalpy, you actually had to calculate the delta in this case TF, I think, in the assessment just delta T. All right, I hope that helps. Thanks for watching. Have a good day.